And so we're gonna start in just a few minutes, but before that, please make sure that you check out our YouTube channel. This is our Can Monthly Journal Club, and I'm host Twinkle. And so we have a YouTube where we upload every month's journal club, and we have like 3 or 4 years of archives going back of different things. And one of the nice things about the journal club is we get to, since we do it so frequently, we get to have a lot of like new and cutting edge research coming up as it's coming out. And so it's kind of cool to look back at our archive too and see how we've come as a subdivision and as an industry. So please check out our YouTube channel. It's Can and the Cannabis Chemistry Subdivision on YouTube. And you can also find us on Instagram at can_ACS. And that's where we will be posting all of our future journal club announcements and other things like that. And then Alex, also, if you want to plug any of your channels or things, you can do it now and we'll do it again at the end.
Yeah, you can find me mainly on Instagram. It's Alex Eckman Canna. And then on LinkedIn as well. Feel free to send a connection request and message me on LinkedIn as well.
Great. Okay, so we are going to start today. Thank you everyone for joining us this Thursday before the holiday season begins. We have Alex here today, and he is a recent grad from Lake Superior State University's Cannabis Chemistry Program, one of the first of its kind in our country, and he's also a veteran of the cannabis industry in so many other ways. And he's here to talk to us today about research that began when he was working on heavy metal detection optimization, and it really became its own project. So he's going to share his progress with us. And I will let you take it away, Alex. Thank you.
Thanks, Twinkle. I appreciate it. You guys able to see this just fine?
I can see it. I think so.
All right, perfect. So as Twinkle had mentioned, this is some interesting findings as a part of my senior capstone research project, where we initially were looking to develop a novel means of heavy metal analysis in cannabis vapes using a scanning electron microscope. And as we'll see here in a bit, the reason as to why we were going to do that. But we'll start off with just a quick intro here. And it looks like it wanted to autoplay, so that's interesting. But pretty much there are 3 different types of cannabis vape hardware. We've got the 510 threaded vape cart up here at the top left. That's one of your more common ones. Below that is the pod type vaporizer. And then as well, we have the disposable vapes. So just getting into a little bit of the background of what these cannabis vapes are really made of. We see here in this figure, there's a handful of different components. Mainly we have a porous ceramic wick that surrounds a atomizer. That atomizer can contain a handful of different metals that act as a heating element to actually heat up your distillate, live resin, whatever cannabis oil is inside of the vaporizer. You generally have a polymer constructed reservoir tank or a glass borosilicate tank as well. And then we have a vapor path for the vapor to actually travel into the mouthpiece. And then just getting into a little bit of the basics of polymers. There's tons of different classes of polymers, polyesters being a large class. And they're really just polymers linked together by ester bonds. And polymers can be thought of kind of like a large chain of Legos, where different monomers can kind of build up the polymer chain. And in most of the polyesters, we see this diacid here is kind of your main building block. In our case, we have terephthalic acid, and we have these different diols that we can add onto that main building block. And what we get are various polyesters on the back end of that. So if we have this terephthalic acid and we put in some ethylene glycol, which we can see the structure down here at the bottom left, we get PET, which is very common in water bottles. If we add a little bit of this cyclohexane dimethanol ring structure, We get PETG, also very common in water bottles. But if we change which one of those monomer diols is the major compared to the other one in molar ratio, we get what's called PCTG. This was commonly used in vape carts for a while. And then if we add this other structure right here, this tetramethyl cyclobutane diol, we get what's called PCTT. And this is just giving some introduction to the various polymers that we've seen used in the vape industry. And as we can see here, PETG was the early generation of vapes, more so in electronic cigarettes, and they were prone to cracking based on the different constituents of the e-juice, actually. So the industry switched to PCTG based on what they believed was improved chemical resistance and strength. However, that was still found to be a suboptimal polymer with potential leaching concerns. And so recently, the industry switched to this PCTT, and we can see the structure here on the bottom right. The thought was that having a blockier ring structure in here is going to change how the polymer chains stack on top of each other. And that's going to alter different things like the crystalline versus amorphous properties, different chemical and heat resistance properties. And so this was probably back in 2023, from what I found, the industry switched to this PCTT polymer. And as we are about to find out, it potentially may not be the perfect polymer to use. So getting into our original research design, this was off of the back of some published research that showed that the current means of heavy metal methods may have reproducibility issue based on the particle size. And I'm going to butcher his name if I pronounce this here. So there is a link to the original study there. But what we thought we could do is simply dissolve the contents of a vape in some hexane. We would then pass that through a nitrocellulose filter, which would catch any of the particles that would potentially have leached out into the distillate or vape oil. We would simply remove the solvent and then place our filter under our newly acquired scanning electron microscope and utilize the EDS particle analysis software to count and characterize any of the retained particles. But as we see here in this photo on the right, I kept getting an interesting precipitant from a handful of the vape carts. Now, being in the industry for many years, I had dissolved vape carts. I originally thought that this could be a lipid, but we were using hexane as our solvent, so that wouldn't make sense based on the solubility principles. And the big thing was this unknown precipitant was actually volatilizing under our scanning electron microscope beam. So not wanting to damage the new SEM, we figured we would take a step back and actually try to figure out what this was. And that refocused our research aim to, one, isolate the unknown precipitant. We wanted to quantify how much was actually coming out and then identify what it was. Our early hypothesis was it was potential polymer leaching from the vape reservoir, and really kind of repeating what I had already mentioned. The goal then was just to remove the vape oil. We would isolate it, centrifuge, and filter it. That was really just to clean up any cannabinoids or terpenes that could be retained in the polymer. And then, the unknown. We then wanted to do a gravimetric analysis of that recovered mass to really quantify how much was actually there, and then do a variety of tests to really identify what it was. So starting off, we obtained the mass of the vape when it was full. We emptied it using gravity over the course of 24 hours. I didn't want to introduce any additional heat or solvent that would further potentially degrade. So simply just caught all of our cannabis oil in a centrifuge tube, dissolved it in some hexane, and as we can see here, that pretty reliably precipitated out any of that unknown. went ahead and centrifuged the unknown, decanted the solvent, and just repeated that again to wash any cannabinoids or terpenes off of that precipitate pellet. Now, with the gravimetric analysis, we obtained the mass of a dried filter. We would then go ahead and filter the pellet out of that centrifuge tube, remove our solvent and dry the pellet, and obtain the mass of the dried filter and pellet after the fact. We had a relatively small sample size. I will note that ahead of time, a 8 vape sample size, 7 of those being polymer construction reservoirs. They were of the disposable vape type, and that was just obtained through a local CBD vape shop. The average precipitant recovered of those 7 polymer vapes was 4.8 milligrams, representing an average weight by weight percent basis of 0.82%. The maximum precipitant recovered was from vape number 4. That was 9.7 milligrams, representing a 1.58% weight by weight percent basis. And then when we look at which one was the worst on a weight by weight percent basis, that was actually going to be vape number 5, where 1.61% of the distillate that we took out of the vape actually contained this unknown precipitant. So that was certainly a cause for alarm. We went ahead and got some microscopic photos of it, threw it under the stereoscope and various bright field, dark field microscopes, just to kind of really take a look at what we had. Now, it didn't really provide much definitive evidence at all. So we took a look under the scanning electron microscope, which we can see are these photos at the bottom. The interesting thing that we really saw here, if anything, was this bright white speck on the backscatter in composition mode. And that's really because the SEM has atomic level contrast brightness, meaning that different elemental weights are going to show up as a different brightness. And when we ran a particle analysis on that white speck there, it was actually a aluminum particle that was caught in the pellet. And so really not getting too much data from these other than some pretty SEM photos. We moved on to taking a look at the physical properties. Started off by doing a melting point analysis, realizing that this is not the ideal way to do a like melting point on polymers. Ideally, we would have thermogravimetric analysis or DTC, but we were just utilizing what the university had. So went ahead and got a rough range for the melting point and flow point. Looking into next, we wanted to see what this would dissolve into. We knew it didn't dissolve in hexane because that was the original solvent we were using. And after testing a wide range of solvents, we found that the only thing that would dissolve in was chloroform, which was actually handy because we needed that for NMR. But we'll save that for a second. The next thing that we did is we took a FTIR spectra of it. And what FTIR does essentially is it shows us functional groups. And this was helping us now get a better picture of what the molecular structure may look like. And we found a handful of pretty key stretches here. And then when comparing it to a known spectra of PCTT in literature, we find almost identical overlap. But this was the first kind of indication that we could have a polyester, mainly based off of the carbonyl and carbon oxygen stretches that we observed. The next thing that we did was we actually collaborated with an external collaborator to do Raman IR, and Dr. Vernon was able to find these interesting peak overlaps between what our unknown precipitant was and scrapes of the exterior vape reservoir. So our thought process on this was we would try to see if the spectra from the unknown precipitant matches up with what we know to be the exterior of the tank. And outside of a handful of peaks, these three that are underlined by the arrows, we have a really good match here. And that further kind of pointed us to potentially having some leaching from the reservoir. Now, we still don't know what these peaks are, but it's potentially a contamination is what we think in the sample. What we were able to really use to definitively tell us the structure was a host of NMR analysis using 1D and 2D NMR. And right here, I just took a screenshot of our carbon NMR and went ahead and overlaid the structure with the numbers of these peaks representing what carbon we assigned on the structure. We also have a hydrogen NMR, DEPT, COSY, and then HMBC. But really, the NMR mixed with the other spectroscopic methods allowed us to pretty definitively say that we've got evidence of PCTT leaching in these brand new unused vape cartridges, which was certainly cause for concern and very interesting. Suggesting a plausible mechanism, this is where I think further research definitely needs to be done, and I think it would be really interesting to dive into this more, because we know that terpenes can act as a solvent, but the unknown precipitant, which we identified as PCTT, is only soluble in chloroform that we found. So it really makes me wonder what is actually acting as the mechanism for dissolving this. The other thing too was, although our sample size was incredibly small, we did notice that contact time was a driver for leaching, with the higher leaching vapes being aged above 250 or so days. And it seemed to be a exponential rate of return on the leaching after about that year point. So we don't really know if it's a cannabinoid, a terpene, or just contact time causing this, but I think it's a cause for future research. And I'm definitely hoping that a student is willing to kind of take this research on, because a lot of this is kind of, or a lot of students do have the ability to do that at Lake State. So certainly excited to kind of keep watching and seeing what comes of this. We are currently working on getting this published in ACS Omega. And so I'm definitely really excited for when that comes as well.
Great job. Thank you so much for sharing that with us, Alex. That's really interesting. I wanted to ask, how long did it take you to collect all of this data?
So we started probably in the summer of 2024, and we finalized it probably April of this year. So it took a good amount of time. We did also grab stuff like NMR and FTIR, comparing the precipitant on the inside and then the vape tank on the outside, kind of like how I mentioned that we did with the ramen. So we just tried to put as much supporting evidence as possible so that we could really feel that we believe we have what we say we have. And it definitely, it took a while. Lake State is by no means an R1 research university, as much as I wish it was. So it's a small university of about 1,400 people, only a handful of professors, but I'm very thankful and grateful for their time for helping me along with that. Dr. Wright, Professor Southwell, and Dr. Mosey all helped out tremendously, as well as Nicholas Gordon as well. So I definitely have to acknowledge their help.
That's incredible. I was blown away by the amount of supporting research. We don't usually get to see so many different techniques and variations in cannabis chemistry because we're so sequestered to either industry or black market research. And so this is really exciting that not an R1 university could produce so many different methods of validation. Also, if anyone else has questions for Alex, this is a good time
please.
to put them in the chat. Yeah. But I'm just like, I'm so blown away. That's I know it's felt like forever, I'm sure, but that is not a long time in the way that research moves. Even at R1 universities, there is so much, especially with the current political climate and the funding, the state of funding, like that is a really impressive amount of data to have collected in such a short amount of time. And it just goes to show, what the industry should be striving towards, both in academia and in the private industry. So I think this is a really great example. Thank you.
Thank you. I really appreciate that. And it definitely was fun. I feel like because we had all those instruments available to us, it was like, why not utilize as much as we can and put as much information into the research? I wish that we had more, like a Maldi Toff to get molecular weight or stuff like that would be amazing. But I think with what we had, I'm really excited for the outcome of the research.
Yeah, no, that's very cool. And I think like it's just cool. It's honestly, it's a cool flex for the cannabis industry to be able to have access to all of this different kind of instrumentation and use it for this, because so many times we see papers published and everyone who reads that paper, the first question is like, okay, but can we do this experiment? Can we also get this data? And a lot of times it's just not super feasible. So I think this is really exciting. What was your experience like at Lake State? Did you guys get to work with industry partners or like collaborators outside of the academic system? Could you talk about that?
Yeah, certainly. There's a handful of partners that the university has from the Michigan cannabis space, as well as, I guess, on the nationwide side. Ones that come to mind: Cambium Analytica is a testing lab. We have the Lions Lab Institute. Day Savers is a rolling paper company, as well as custom cones that we've worked with. Low Temp has donated equipment. We every year are thankful enough to be sent out to various trade shows and conferences such as Benzinga and MJ BizCon. Through that, we're able to really connect with a lot of the industry. It was actually at MJ BizCon last year where I started slowly showing maybe like screenshots of the precipitant coming out and slowly getting the word out about this research. Through that, we were connected with the Vape Safer initiative, which is a group of hardware manufacturers in the vape side of things. And they had mentioned that they were actually aware of this problem, and they were taking steps to try and look at new materials to utilize on the polymer side of things. So I would say that Lake State, whether it's connecting us through in-person networking events or just bringing in guest speakers for various classes, bringing in industry equipment that you would actually utilize when you go out to the workforce, they do a really good job of supplementing all three of those. And it's really kind of up to the student then to embrace that and really take that opportunity to the next level.
That's very cool. So inspiring.
Thank you.
It's cool to see universities investing in that and prioritizing that for our industry. I'm so excited. Emma David wants to know, she says, cannabis research can get tricky. What was your biggest hurdle and what is still needed to make this kind of research easier to conduct?
That's a really good one. There was a couple hurdles along the way, and it really came down to, we have to be very careful how we navigate this research because we are a federally funded campus. So with that being said, all of our stuff that we were looking at was either CBD derived, hemp bill compliant. And like, you had to be really careful. What happens if you have a THCA hemp bill compliant compound and you decarboxylate that on campus? Now you're in some really dicey territory. So it was just being really aware of what you're doing, making sure that you're not going to put the university in any kind of bad implications when it comes to legal laws around cannabis still being a Schedule One substance and this being a federally funded university. And I think the professors do a really good job at one, monitoring and policing that, but also holding your hand, helping you develop projects that you could do that's still applicable to both the cannabis and hemp side. But it definitely was a challenge. I know I had a handful of research projects kind of shot down because we were worried that it may tiptoe that line. And while it's sad to see, I can understand it. You don't want to put anyone at jeopardy, especially being a small university. But that would probably be the biggest hurdle, was just making sure that we stayed compliant. Especially because, like, we're starting to get the word out about this university and what we're doing. It would be very easy for a regulator to pop their head in and ask some questions, take a look. I mean, we're growing on campus. We've got a full extraction lab on campus, and then everything that's grown gets extracted. Everything that's extracted then gets destroyed as analysis or research. There's a full Agilent compliance lab on campus. So we can really experience all sorts of different sides of the industry. We just kind of have to be a little careful about how we do it.
Wow, that makes a lot of sense. That sounds a lot like some of the challenges that I'm sure you'll continue to face when you're working in the industry and outside of academia, because we are, even though we're a legal industry in many states, there are still a lot of lines that we have to be careful about, and the way that we conduct research as scientists and the way that we share that information with the public is under a lot of scrutiny. And so it's interesting to see that the next generation of scientists coming into the industry will have already experienced some of that as they come in, and hopefully help us take it in a better direction. I think Emma wanted to know also, what do you think is still needed to make this kind of research easier to conduct?
I mean, the first thing that comes to mind is just rescheduling or descheduling. Ideally, just loosen the barriers on research. I know even in Michigan, we've got a research license at the state level, but the way that it's written, you have to have a DEA license, which is nearly impossible to get, especially for our university. They've been trying for many, many years to get their hands on both of those. And it's just very burdensome and cumbersome. So I think taking some of the red tape out and just reducing the regulations behind it. At the end of the day, this is a plant. We just want to learn more about it. It's not like we're trying to produce or back channel stuff through regulated sales. This is just research. So I think the easier we can make it, the better.
That makes a lot of sense. So we have some more questions, but before we get to that, you just recently graduated, right? So are you able to still have some involvement in the program? If someone did, you said you hope someone would pick up this research. If someone did pick this up, you would be able to help offer guidance to them too?
Yeah, certainly. I'm still living just right down the road from the university. And the nice thing about it being a small university is we got really, really close with the professors and the administrators. So, it's to the point where I've got their phone numbers and I'm texting, calling them every once in a while. But it would be very easy for me just to jump on a Zoom call, even if I wasn't local, and help out. I think that would be something that would really intrigue me, because I think there's a lot of different projects that could stem off of this, and research in general is always just building on the shoulders of giants. So I would love to see this kind of build and expand.
Yeah, that's so interesting because they've already got everything ready in the infrastructure, and that is the number one challenge in the cannabis industry now, is having the ability to do the research either legally or having access to the instrumentation. And so that is super exciting. Peyton says this is amazing research. Do you have any information about how these vapes were filled? I wonder if the fill temperature or potentially fill needle abrasion materials play a role.
So I don't actually. That's a really interesting question. I know that we have actually obtained a couple of those fill needles. It was for a different project and trying to track down the source of some of the contamination. And we did find some damage over time on those fill needles. But as far as how they were produced, we don't know. But what we do know is that they did have heavy metal compliance testing beforehand, and they did have COAs at least provided by the manufacturer. Now, we don't know how valid those COAs are, so we didn't put a lot of weight into them, but that's how we were really able to at least kind of track the shelf life or how old these were, was by just referencing the manufacturing date on the COAs and taking a look at what metals were present on that COA.
You said you had 8 different vapes. Were they from 8 different manufacturers?
So I'd have to go back and take a look. I believe there was 3 different manufacturers because we tried to get at least one of every style, being a 510, a pod, and then a disposable. We didn't have a lot of availability around us locally, so that was a little bit of a hindrance, as well as with this being a student project, we were budget constrained. I would love to repeat this with a sample size of maybe 40 or 50 vapes and get a better look at that from a statistical side, especially when we're seeing kind of larger numbers on that gravimetric analysis, upwards of 1.5% on a weight by weight basis. So I think our sample size was small, and that was a limitation, but including more brands is never going to hurt.
Yeah. Well, that's nice that you were able to get different styles. So in theory, they were all probably filled slightly differently during the manufacturing process also. Kyle wants to know, he says, in relation to the metal content in the emissions, I was wondering if the same lab was involved in testing the oils before they were added to the vape in question. So basically, are the COAs for the final product coming from the same lab as the COA from the individual parts of the product?
No. So it would have been different laboratories that the that the brand manufacturers sourced. So for example, if we had 2 different companies, one for the disposable, one for the 510, they definitely utilize different laboratories for their testing. And because we pivoted our research aim to identifying what the unknown precipitant was, as opposed to actual method validation for the heavy metals, we didn't actually definitively validate those on our end. So we're unreally able to speak too much on the metal leaching other than we observed it. And that would be something where I would hope that a student would be able to take this research and bring it forward with an actual method validation, because I think the SEM method is an interesting approach. I don't know how much industry would utilize it because of the cost of an SEM, but if you were able to really mitigate the microplastic volatilizing under the electron beam issue, it is an interesting approach, I think, at least in theory.
That makes sense. Kyle is saying that most extraction equipment is made of metal. He wonders if there's possible contamination at parts previous to filling the vapes where contamination could be happening. And I think that, that is a great question. And I think you're going to have to work directly with some manufacturers to be able to pinpoint where contamination could be coming from if it is being introduced. But I think that showing that it's present in a lot of different brands and a lot of different vapes really speaks to the widespread nature of it. And what that indicates is there's definitely a problem at some point in the process for a lot of people. And so it could be happening in multiple ways and compiling, or, and I think this is extra tricky because if this is all coming from things that are Farm Bill compliant, they probably just generally have less testing and less regulated testing than things in the legal market. And so people are going to have less COAs and less process control throughout that's documented.
Certainly. And then a lot of people don't do final form testing when they're looking at COAs. They're just pulling a little bit of a sample out of a 1 or 5 liter beaker and testing maybe high up in the beaker, halfway down, and at the bottom of the beaker. They're not testing the vapes after it sits for a handful of months. And so you certainly could do a handful of tests right when it's out of your distillate rig, and then maybe do another test after you fill it, and a test maybe 3 months down the road, and that would help identify if it's coming from your vape cart filler or if it's coming from the actual vape hardware itself.
That's a great idea. Alex Jensen says that aerosol testing could also be useful, which would be...
Yes, that was one thing that probably why this study has been limped along. I have been trying to source a actual aerosol, like fake one vape tester for a while now. We potentially are able to borrow the Cannabis Research Coalition's, but we just haven't been able to connect the dots on actually getting our hands on one. We looked into potentially buying one, but it's just cost prohibitive for the university at the moment. So that was definitely something that I wanted to look at, because we know that these metals are leaching and that these polymers are leaching, but we don't know if it's entering the vapor stream. It's very possible that the porous ceramic wick acts as a filter and entraps or keeps those metal particles from entering the vapor stream. And really the only way to know that would be with aerosol testing. Now, I would hypothesize that the microplastics are probably volatilizing just simply based on melting point temperatures. But again, that would be something that an aerosol test would really allow us to definitively say.
Does anybody else who is a part of VapeSafe have capabilities like that? Or are they mostly other academics and researchers who are joining together? Or are they like a group of manufacturers?
So I don't know if they do have that capability or not. As far as I know, and it was off of just one short meeting with them, they're a group of manufacturers on the hardware side that are just coming together to try and share information and help improve vape safety. And I definitely need to get back on a call with them, come to think about that. But as far as I know, I don't know if they have the testing capabilities or if they just outsource that to academic institutions.
Yeah. That's so interesting, though. It's interesting also how you mentioned that the industry has had a couple different waves of materials that go through and that are adopted widespread. That's really interesting, because as someone who doesn't have much to do with vape hardware, it's not something that I would have thought about, which is how are different manufacturers and competitors sharing or not sharing proprietary information that then relates to safety. And Kyle saying that ASTM has suggested that aerosol testing needs to be standardized to ensure results are cross-comparable, that makes a lot of sense too, because I'm sure all these different all these hardware manufacturers have their own standards for internal testing that is variable.
Yeah, I would totally agree.
So we have someone in the chat who says that they've built an inhalation testing machine inspired by an ISO method. So,
oh, that's awesome.
That's great. If anyone else has more questions, please dump them now. Otherwise, I will let, oh yeah, we have one more. Alex says, was triethyl citrate used as a diluent or emulsifier in the vape mixes?
Now that I don't know. We do still have samples of all of those cartridges that we analyzed. We didn't actually take a look at the constituents of the distillate. When it comes to looking for any dilutants in there, it was all based off of the manufacturer's COA, basically showing cannabinoid terpene percentages. But that would be something that I'd be curious to look into, and I'll actually keep that as a little side note to do some more research in that, because we did not. It was more so just trying to identify what we had actually coming out, and then once we knew that, we could build future research off of it.
That makes a lot of sense. I'm pretty sure you can see triethyl citrate with a regular GCMS. So if you guys
Okay.
still have
Yeah.
samples, could be pretty easy to do.
Yeah, absolutely.
Thank you so much, Alex. Yeah. And other Alex for asking that question. Thank you guys. If you want to go ahead and do some plugs and stuff, this video will appear on our YouTube within the next 2 weeks. And thank you so much for sharing your time.
Yeah, thank you again for having me. I always love jumping on these, and any chance that I can help spread the word and educate, I'm always down for. If you have any other questions or anyone watching this down the road, feel free to reach out to me. Like I said in the beginning of this, Instagram, Alex Eckman Canna, or LinkedIn are both great avenues. I tend to usually get back to you that day, but thank you again for having me. And also, if anyone out there is interested in learning more about Lake Superior State University and the 2 bachelor programs that they offer, I definitely encourage you to take a look at lssu.edu. I'm also happy to answer any questions that may pop up, but I definitely want to give a shout out to Lake State for really offering this degree and giving the students the opportunity to do research like this.
Great. Thank you so much, Alex. Everyone, we will be back with Journal Club again next month on the 18th. So look out for a reminder about that. And we'll have Dr. Allison Justice joining us. And I hope you guys all have a great rest of your day. Thank you.